Okay, so question B3 on the 2018 Leaving Certificate Design and Communication Graphics, Section B of Higher Level. So, first of all, the first thing we do to tackle this question is read the question carefully. So, we have to do that in order to appraise it. And what appraising is essentially just um, debunking or analyzing the question, trying to find out what they're asking us to do. And in order to do that is just simply read it. So the image on the right shows a piece of roadside sculpture in the form of a steel hedgehog. So that's the steel hedgehog right there, which is located on the M11 in County Wexford. Okay. It comprises a series of planar surfaces. Okay, so straight away we know that's what the question's going to be about, planar surfaces, each carefully angled to allow for the runoff of rainwater. Okay. Figure B3 shows the plan and elevation, so that's figure B3 right there. Shows the plan, elevation, of four such intersecting surfaces. So the four surfaces they're talking about here is ACG here, the triangle, ACB, another triangle, and AGFE, that's a four-sided polygon, and AEDB, another four-sided polygon. So there we have those intersecting surfaces. The figure and vertical coordinates for points A, B, C, D, E, G, defining the four planes, are also given. Okay, we see on the right hand side all the locations of all our points. So the way we read these is we start off from the XY line. The first number here is going to be how far in the page we go horizontally. So it's the X value. Then the 60 over here, the middle one, is going to be the Y value. And the 45 is going to be the Z value. So if you want to think of it on the page, you go in, up, then down. And it's the same case for each one. So for example, for B, you go in to 110, you go up 35, you mark your point, and you go down. From the XY line, you go down 80, and you mark your point. So you do that for all the letters as shown, but we don't have F yet. So in order to get F, I presume that we will get it later on in the question. Well, first of all, we do first things first, which is just do what the question asks us to do. So, A there. Draw the given elevation and plan of the intersecting planes ABC and ABDE. So, given elevation plan. Okay, so we see ABC here and ABDE. So we draw these two first. We forget about G and F for the first part of the question. So we see here ABC as well and ABDE. Okay, so we draw that first. So going on to the solution, this is how we go about doing that. So just before we start, we want to start somewhere around the center of the page. I did it slightly off to the right, but yeah, around the center of the page, it's a good place to start. Just because we know that it's going to be, as said previously, an intersecting surfaces. So we're going to do intersecting planes, and that question always involves some sort of auxiliary view. So just to make sure that we don't lose any space on the page, it's a safe call to go start somewhere around the center. So starting off the question, we draw our XY line, obviously, and we label it, and we just start plotting our points. So going back to the question, we start plotting A, B, C, D, E, G. So in 145, up 60, down 45. In 145, up 60, mark, down 45, mark. And we do that for all of the letters as shown. So I started off with all my points in elevation and label each one. There we have it. So A, B, C, D, E, and we don't do G yet actually, because going back to the question, they're asking us A, B, C, and A, B, D, E. So we have A, B, C here and A, B, D, E. So we just join all those together. Just simply join the dots. Nothing too complicated here so far. So, oh, almost. Okay, so we have our plan and elevation so far. Oh, that's part A done. Next part of the question. We go back to the question slide. Determine the dihedral angle between the planes ABC and ABDE. So straight away, as we know, the dihedral angle is the angle between the two planes. So how do we find this angle? First, we want to find the true shape of our intersecting plane ABC and ABDE. So looking at that, just looking at the question, our common line is what we need to find the true length of, first of all, and then we have to find it in a point view. So, yeah, looking at the question, ABC and ABDE, we can see that the common line here is AB and AB. So AB will be the line that we need to find the true length of, as seen on the image here. So we see the vertical plane here. That's our elevation of the question. So this right there, and our plan of the question on a horizontal plane is going to look like this. So we got that much. And what we need to find is our AB line as a true length. So our AB line, we're going to be working with feature cannot move itself. Okay. What we're going to be working with is these two planes right here. So what we're trying to find is this line right here as its true length. Sorry. So we don't see it as a true length so far, because we need to look at it from a different angle. So we have to rotate ourselves to put ourselves on a new XY line, so that the new AB line will show us the true length of it. So how we do that is we rotate ourselves using a auxiliary. Okay, so we can see that in the 3D solution as well. We need to find ourselves looking at the AB, this purple line right here. That's the true length line. So we can see these two, and we just need to rotate ourselves around. And how we do that is we just get rid of these planes for a second so we can actually look. And let's see, which way? Is it something like that way, I believe? No, the other way, like this. Yeah, so we should end up something like this after we've done our auxiliary, and we'll get to that in a minute. And this will give us our true length of AB. So how do we go about finding the true length of AB? So we go back to our drawing. Let's see, presentation, go back to our drawing. We have all our points here. And we see the line AB. We need to draw an XY line parallel to it. And that's what's going to give us our points perpendicular to it. So we get our new X1, Y1 line. We get our sliding set squares, slide it up to the AB line, and we translate it over to the side. The distance doesn't really matter as long as it's past this D mark here, and we label it x1, y1. So that's going to be our new view of us rotating ourselves to find the true length of AB. So finding the AB, or yeah, finding the true length. So how we find the points on our new auxiliary line is we use a method called the 1-2 rule, or 2 views back, as I like to say. So that's a rule that has to be taught, because you always have to go 2 views back in order to find your lengths for your points on the auxiliary. So to better explain myself using that is we bring down all our points first of all, ABC and ABDE, and these points are perpendicular to the x1 y1 line always. So we extended all these lines out first of all. Then we bring our compass to get the same dimensions from our 2 views back. So this is our view. We go back 1 view and we go back 2 views. So back to the elevation. And we measure from the XY line all the way up to the point, vertically up. We get that measurement using our compass. We bring that compass back to our new x1, y1 line, and we mark off a point. And once we have this point, we repeat the process for all the other points as well, just to give us our true length of AB. So here we see we found E, A, D, C, and B. And once again, we just join up all the dots. And why do we do that? It's because we're trying to find AB as not an edge view, but as a point. So first of all, we need to find it as a true length line. So as we see, we just connect up all the dots again. Going back to our SolidWorks, there we have it. That's our true length line. And now what we're trying to do is rotate it once again. So we have it like this. As we can see in the solution, we have it like this. And what we're trying to do with this purple line is turn it into a point. So how do we do that? We do the exact same thing once again. Instead of going parallel to the AB line, we go perpendicular to the AB line, the true length of the AB line. And we draw x2, y2, sorry, again. And that turns any true length line into a point. So that's what we're trying to find, because that's the common line between ABDE and ABC. And that should give us our true length angle. So as we can see in the solution, we have AB here, and we just flip it around 90 degrees perpendicular to it. And I'll just change the scene so you can see it better. We can see this will be our what is it? ABED. It's gonna be like this actually. So here's gonna be our points AB, D and E, and our point C right here. And this will give us our true angle like that. So going back to our presentation, how do we find that? Let's see. So we have all our points, and we have our AB true length line plotted out, and we do another auxiliary, this time perpendicular to the AB line. Let's see. Yep, and we call it x2, y2. We always label our new auxiliary xy lines accordingly. So what we do next is the exact same process as we did before. Using our 1-2 rule, or our 2 views back, we bring across all the points, bring across all the points, bring across all the points, always perpendicular to the XY line. So we do that first. Bring up all your points, bring up all your points. And once we have all our points, we go 2 views back. So we go 1, 2, and we take our measurements from our x1, y1 and the two views back. So once again, just taking our compass, taking the measurements, for example D there, taking the measurements, striking it off on your on the D that you extended, on the x2 y2 line this time, and we mark our points, and we repeat the process for every point. So we take E, strike it off, AB. We extend the line AB right here, so they obviously align in the same line, and it just so happens that they both have the same measurement from the x1 y1, same measurement. So that's how we find our point view of AB. And see there to finish it off. Next up, we just join all the dots to give us our ABDE as an edge view and our ABC as an edge view. And why this works is because both lines are true shape, or both lines are true length, should I say. This gives us our true length. This gives us our true length. And the common line is seen as a point. So this angle right here that it gives us must be a true angle, the true dihedral angle. So we just draw it in with our compass, and we mark it off with a symbol like that. And that's the symbol we use for the dihedral angle. So next part of the question. Back to the question. We have located the dihedral angle ABC and ABDE. Now, part C of the question. First of all, we draw the point G in the planet elevation and determine the distance between points G and B. So back to our solution. Go back to the very, very start of the elevation, finishing off that point G. We find our point G in the planet elevation, and now finding the distance between G and B. So the method we use is called a rabattement. And what a rabattement is basically getting the point. So what we have to do is find GB as a horizontal line in the plan, because when it's a horizontal line in the plan, it's going to be true length in the elevation, and that's what we're trying to find. So how do we get this GB line that isn't straight, or that isn't horizontal, into a horizontal position? We use a method called the rabattement. And how a rabattement works is we just simply take our compass and what do we do with the compass? We bring it all the way up until it reaches a horizontal point, just like that. We bring that up into our elevation. We bring the line across from B until it hits that line that was brought up, and we just simply join G back to that line, and this line from G to B gives us our true length. Yep, that's it. So that's the true length part of the question done. So we have AB, half of C done. What else does question C ask us? The opposite edges AE and GF, so we see AE and GF of the surface AEFG, yep, are parallel. Okay, good to know. Complete the elevation and plan of the surfaces AEFG and ACG. So we see AEFG here and ACG right there. So completing the entire elevation, we see that AE and GF are parallel and AE and GF are parallel. Obviously, if they're parallel in the plan, they're going to be parallel in the elevation also. So back to our solution. So the next part of the question is our sliding set squares. So we line up our sliding set squares with the A and E, and we know that G and F are parallel. A, E, G, F are parallel. So We slide it up to A and E, and we slide it all the way up until it reaches G, and we draw in our light line so far, and we bring the other one directly up because we know that E and F are also vertical. So we found our point F in the elevation now. All we have to do is repeat the process in the plan. So once again, we get our sliding set squares, line it up to A and D, and we just slide it up until it reaches G in the plan, and we just mark in our F lines. And that gives us our entire plan and elevation. Fully completed. Right, so back to the question. Complete the elevation and plan. Okay, that's completed. So A, B, C completed. Now part D, last part of the question. So we'll do that first part of D first. We'll touch the plane AFG at the point which is 55 millimeters from C. So going back to our question, we have all this done. And the last part of the question. So this is going to be our pink line here. So first of all, what we do is we know that it's going to be a horizontal line. So we draw a horizontal line either way until it hits our plane. What is it? F, G, A, E on both sides of it. Okay. And we bring that down all the way and join it back up. So where it hits A, G, F, E in the plane. Not in the plane, in the plan. We join it back up to F because it's joined up to F up here. And what we do is we measure out 55. We know that it's going to be 55. And so we get our point here, 55 millimeters from C. Yep, that's our point P. We bring that down into the plan. Okay, that gives us our point P in the plan. You go from C through point P all the way up to the XY line. Because the way you draw a line is you need 2 points. So you have your point C, point P, and you can just extend it through. And what did the question say? The question said, plane, yep. Hence, determine and indicate in degrees the true angle between this horizontal line and the vertical plane. So, the point where it hits the XY line, going back to our 3D solution, this is the vertical plane. So, where it hits the XY line is also where it hits the vertical plane, as we see, right? Because the line goes all the way up, like horizontal, all the way. Oh, it hits the XY line here. That's the vertical plane. So, going back to our solution. Where are we? Oh yeah. Oops. Our point P, join it up, and there we have the angle where it hits. I want to get this terminology right. The true angle between this true horizontal line, yep, and the vertical plane, yep. So we mark off our angle, and it is 53 degrees measured with our protractor. We joined that up, and that is our question completely finished. And here's our 3D solution that we were looking at. So yeah, 53 degrees, our 2-point P's. Yeah, we've seen all that in our 3D model. Let's just appraise the question before we finish up. So the principles that were tested in this question was finding the true shape and true angle of lines and shapes. So the true length was here, true points, I guess, true lengths. Auxiliaries and true lengths and true shapes, they go hand in hand. So there was another true length using a different method here. That was our rebatment method, with using the compass, bringing the lines across, getting it horizontal in the plan, and true length in the elevation. So locating missing points using sliding set squares, that was also part of the question. So obviously AE and GF, We had to use sliding set squares to find f, both in plan and elevation, and finding traces. So obviously 55 from point C, we got our points. We had to use a trace of C where it hit GA in the elevation, had to bring it down. It found our trace GA in the plan, and we had to join it back up to F, and that gave us our point P in the plan. And we just joined from C to P all the way up to the vertical plane, and that's how we found our angle. How does this work? So point P, we knew where point P was in the elevation. We didn't know whereabouts point P was in the plan. So we've used the trace that hit AGC, and we brought it all the way down until it reached the point AG. And then we joined it back up to F. It was joined as F in the elevation. It was a horizontal line, so we knew it was a true length line in the plan. And where these 2 points intersected, we knew that gave us our point C, and from C to P all the way up to the vertical plane, that gives us our true angle between the triangle between this horizontal line and the vertical plane. Yep. So that's the horizontal line right there, and the vertical plane, 53 degrees. So that's our question fully completed. Thank you for watching.